Hi everyone, Dr. Waite here, and this is a recording for lecture number 2, January 23rd, 2013. This is Engineering Economy. As I mentioned before, class is online today, and if you're watching this video, I think you must have got the message and found the link, so congratulations, you've made it, you're in the right place. Looking at our announcements, remember that homework number 1 originally was on the class schedule that I handed out, was going to be due today, the 23rd. But I realized that that was an error and that you need more time to solve that, and so I've postponed the due date to homework number 1 until the 28th of January. And I made that announcement in class last time that the way we're going to do it is have the homework be due on Monday. And since we don't have class meetings on Monday, you can submit that any number of ways. You can slide it under my office door, you can give it to me personally, you can send me an email with a scan of the assignment to waite@marshall.edu, my email address that's listed on the syllabus. Just get it to me however is most convenient for you before 5 p.m. on Monday the 28th. And then what that'll allow me to do is look it over and have it graded so I can give it back to you on Wednesday the 30th. And then on Wednesday the 30th, we're going to have a quiz covering some of the concepts that are in today's lecture. That quiz on Wednesday is going to be a way to help determine whether students understood and were able to listen to today's lecture. So today's lecture has several different parts, and I'll remind you that the notes for today's class are posted in the same folder on MU Online as this link is posted, and just to make sure everyone gets it, I'll also send an email that has a PDF of these notes. So in that PDF there's the class notes with some space off to the side for you to write your notes as you listen and learn new concepts, so you can take your handwritten notes in addition to the slides that are there. Also in there is a solution to example 2.4. We're going to work through the example in today's class, and actually what you'll be seeing is called a pencast, and that's me solving the example in real time with a pen, and you can see my pen strokes and hear the audio. Well, what I've also included in the notes is just an ordinary static solution of that animated PDF. This is a static PDF so that at the end you can be sure that what you've solved in that example is the same as what I've solved. And then finally there's an in-class exercise. We're not going to do the in-class exercise together, but what I'd encourage you to do is work through that in-class exercise. It's sort of like an example that I'm not handing you the solution to. Work that as a way to practice and transition into the concepts that are in the homework assignment. You can, the in-class exercise, do that with another student. It's just really for you to get warmed up. It's a warm-up to the homework assignment. Bring that with you to class on Wednesday the 30th. And so that I can see what you did and give you some in-class exercise points. And I mentioned that on the in-class exercise itself. One last thing about today's lecture is there's going to be a capture of me working on Excel. It's all embedded into the same video. So that'll give you hopefully some instruction on how to use spreadsheets. If you're not as familiar with making graphs on spreadsheets, I give you a couple of tips and pointers there. So really all you need to know is that everything for today's class is embedded in this one recording, and as far as visuals and audio, and then the printouts that you should have as you go through this lecture I'll email you, and that same file is going to be posted on MU Online. If you've got any questions, feel free to send me an email and I'll do my best to answer. My email address is waite@marshall.edu. So let's go ahead and get into the lecture. I thought of one last thing I want to tell you before the lecture starts. It's important for you to watch this lecture in as high a resolution as you can for the pencast. Unfortunately, most of the lecture doesn't look that great, and so it wouldn't matter if you watch it in 240 or 360. But when you're watching the pencast, the keystrokes are so small and you want to have as much resolution as possible. So what I'd recommend you do is put it into 1080 and then watch it in full screen, and that way when you're doing the pencast you'll have maximum resolution. So this is a picture of someone charging up an electric car, and we talked on Monday about a comparison between a rundown Dodge Intrepid that doesn't get great gas mileage but that has been long since paid for and is essentially free transportation except for the gas costs and a few other things, compared to purchasing an electric hybrid, a Prius. Well, nowadays there's a lot of attention being given to plug-in hybrids. And so there's the Chevy Bolt, and Toyota's coming out with a plug-in version of the Prius. And the idea behind those types of vehicles is that you can reduce the amount of gasoline that you burn even further if the charge is initially topped up by plugging into your just AC power. And so some of the techniques associated with engineering economy that allow you to compare alternatives can also help you to analyze whether the added expense of paying extra for plug-in capacity is worth the savings in fuel costs that you're going to see. And so, what is the optimal amount that you should be willing to pay for a new car in order to realize certain savings in the recurring costs that one is going to see. So those are some of the concepts that we're going to explore in today's lecture. We left off on Monday with some terminology. Speaking of direct costs and indirect costs, we talked about fixed and variable costs. And so some additional ways at looking at costs of different types of projects and different types of businesses. A sunk cost is a cost that was paid in the past and that doesn't have any relevance to future costs or revenues related to an alternative. And so an example of that is the amount that I paid for that Dodge Intrepid 5 years ago when I bought it. The $3,000 that I paid for it is a sunk cost, and so that was incurred in the past and doesn't have any relevance to how much it's going to, in the future, cost me to maintain and own that car, not in a direct way. Another example of a sunk cost is sometimes when people are selling their vehicles online, you'll see in the ad that they've written, that they recently put new brakes on, or that it has all new tires. The reality is that those are sunk costs, and everyone sort of expects that a car that they buy has brakes, it has tires, and so it doesn't have a lot of relevance from the perspective of the person who's buying that vehicle. Okay, opportunity costs are something that we have to be familiar with, and in addition to the definitions I'm showing on screen here and the brief examples that I'm talking through, remember that in the textbook it goes into additional detail and has some more examples, and so there will be a midterm exam where you have to define terminology such as this, and so it really will be worth your while to familiarize yourself with what the text is saying. So in an opportunity cost, the idea there is that sometimes you don't have unlimited funds, and you can use your limited funds only on a limited number of things. And so if you are going to spend money on one project, you may not have money available to do another project, and you can refer to that lost opportunity as an opportunity cost. And so money that I put into a savings account cannot also be invested in stocks. That's an example of an opportunity cost, is the cost of what could have been done with that money as an alternative to the course of action that I did select. This figure, taken from your book, shows kind of an interesting graph of time and cost. And so what it shows is how much money is spent during a project, and also the potential for savings. And let me just get to a feature so I can point. The cumulative life cycle cost at the beginning of a project, when you're just beginning to try and figure out what the needs are and what kind of equipment ultimately you're going to buy, starting to investigate the alternatives that may be available, that isn't very cost intensive. And so you can see that there's very little cumulative cost at the beginning. And conversely, there's a huge potential for cost savings at the beginning of a project, because compared to a bad alternative, you have lots of flexibility in throwing away bad alternatives and selecting good ones. And so the time for planning is at the beginning of a project. When you get into the next phase, when you begin to do a preliminary design, that requires a little bit more effort. And so that the time and money you spent doing preliminary design does add up to some small cost. It's a small relative to the overall cost of the project. And so if it's a new building on campus that's going to be built, At the beginning phases where you're just doing a preliminary design and some basic prototype testing, still the costs are relatively low, and you still have a big opportunity to save money over the long term. But because you've thrown away some alternatives that may have been cheaper, and you're beginning to commit yourself to a certain course of action, you have less flexibility than you did in the previous phase, and so then the potential for life cycle cost savings is decreased. In consecutive phases of the project, when you're beginning to do the detailed design, there's even more expense associated with that as you begin to produce or construct an item. And then when it begins to actually enter use, you've realized most of the costs that are associated with owning or building an item. There's still going to be maintenance over time, but the further the main idea of this figure is that the further into a project you are, the reduced potential for savings are. And so it's very important to, number one, make good decisions early, but number two, to consider the entire life cycle and not just the initial purchase price, but over the course of the entire project or over the course of the entire item that's going to be built, what all the different phases of your expenses are. If some of you have taken economics before, you know that items can be either used directly by end consumers, or some materials are used by other companies that are generating end products. And so a consumer good may be an iPad, and then a producer good would be the processor that goes into an iPad. And people just don't go off and purchase an A5 processor directly from Foxconn or whoever makes it, but rather Apple buys a series of subcomponents and has a contractor assemble them and call it an Apple product. And so goods can be divided into consumer and producer goods. Utility is a service or a product's ability to satisfy a need or a want. And an example of that, and we're not talking about utilities here in terms of electric and gas and water. A utility means usefulness. And so a product's usefulness can be gauged in terms of how much of a need it satisfies. One company may take iron ore and turn it into steel. And so they've produced some value in doing that. Another company may take that steel and turn it into sheet metal. And then a third company may take sheet metal and turn it into the body panels for a car. And so everywhere, in each one of those steps, a company is adding value, and the utility that they have that is the power that they have to satisfy a need that another company has or another person may have along the way. And so some people get a lot of utility out of having access to Twitter or Facebook. Even though it costs nothing, they get a lot of value, and those services have the power to satisfy a want or a need. Other people don't really get much enjoyment out of social networking, and so that those products or services don't offer them any utility. When we talk about price and demand, independent variables and dependent variables, in any kind of a relationship, one of them is controlled and the other is the output, or is the effect of what is controlled. And so someone who's producing goods has the capacity to determine what price they're going to ask for the item. Now, if the price is too high, of course, nobody may buy it. But the independent variable, that's the input in that relationship, there's a relationship between price and demand. And what goes into that relationship is the price that the producer or the salesman, the seller of the item, tries to ask for the product. Demand is the response to that, and the dependent variable means that the demand depends on the price that's asked. And so we know that if the price of an item increases, then the demand will. And now in the notes, of course, that blank there, you should fill in decrease. And so if the price decreases, demand will increase. And so think of an iPhone. If an iPhone cost $1,000, there would be less demand than when the iPhone costs $49. And so if you were to sketch the relationship, think about on the x-axis, the horizontal axis, you'd have demand. On the vertical axis, you'd have price. And so you need to have some sort of a curve or a line that shows the relationship between price and demand. And so that relationship should look a little bit like this, that when you have high price, demand will be low. And that's what this is showing. High price, low demand. And if you lower the price, then the demand will be greater. Now there's a couple of other things that are shown on this slide. First of all, there's a relationship that's shown here, and it's saying that P is A minus BD. And we're going to talk a little bit more detail on curves that can be used to describe the price and the relationship between demand and different components of price. Other general economic terms is when there's perfect competition in a market where lots of people are able to satisfy a need and there's small restrictions or no barriers to entering the market. That perfect example there may be how easy it is to sell something on eBay. A number of years ago, I sold Bluetooth modules on eBay for Dell computers. And what I would do is I'd call Dell's parts department and I'd order 10 Bluetooth modules for laptops, and it was a real hassle to get through. I mean, it probably took an hour to place the order because you're playing phone tag and all this. And I'd order 10 of them, and they only charged $5 or $6 each, but then I could turn around on eBay and sell them for $20 or $30. And people didn't realize, I guess, that you could call Dell directly. But unfortunately, it was very easy for someone else to enter that market. So there was nothing really stopping someone next door from calling eBay and becoming a reseller of Bluetooth modules as well. So it was very easy for there to be a large number of vendors. And eventually, people were undercutting my price, and so it wasn't worthwhile to even bother any longer. The margins got to be so small. So that's an example of perfect competition. Now, the flip side of that is in a monopoly, it's so hard to deliver the service that or the product is unique enough that only a single supplier or vendor can produce the item, and there's a very big barrier to entering the market. So an example of a monopoly might be a water company where it's so difficult to put the water lines in place. It necessitates tearing up roads, and there's a big expense that comes along with installing a pipe network under the roads and connecting it to people's houses. And people aren't going to want to have 5 or 6 different water lines coming into their home and switching back and forth between whichever one is the cheapest. So that's an example of monopoly. Utilities are often considered monopolies. Many years ago, Microsoft was sued for exercising monopoly power. They were accused of unfairly exploiting a monopoly position and squelching competition in operating systems. And so monopolies are rare because, for one thing, the government has regulations that limit the power and the ability of monopolies to form. When 2 really big companies are going to merge, the government has to often give approval for that merger. Airlines, for example, have to seek regulatory approval for a merger. Oil companies have to seek regulatory approval for mergers. But then the other issue of substitutions means that if a monopoly is charging too high of a price because they're the only supplier, then people will find some other thing. And so if there was an oil company that really was exerting monopoly power and charging $10, $11, $12, $13 a gallon, what people would do is they'd switch to all-electric cars, or they'd switch to natural gas cars. And so people, when the price gets too extreme, will find a way around having to pay that. So usually the market isn't at either one of these extremes. There won't be an unlimited number of vendors entering the market, but there will be more than really it would be considered a monopoly. Think about in cars, and at any one time you could go buy a car from 5 or 10 different producers for any given segment of vehicle that you're interested in buying. All right, so we've talked about some general economics terms, and the variables that we assign to demand is D and price is P. And so if we want to know the total revenue that can be made in selling an item that costs P and there is demand D, so the number of units that are sold, you can fill in the blank there, it's P times D. And so if you have an item that's $1 each and you sell 100 of them, the total revenue would be $1 times 100 or $100. So total revenue is price times demand. So if you consider what happens when you raise the price, remember, the demand decreases. And when you have a very low price, then the demand will increase, but because the price is getting smaller, then the revenue decreases. And so this figure is showing the relationship of both revenue, which is price times the number of units sold, or demand, but it's also showing the fact that the price decreasing means that you're going to be making less for each unit that's sold. So there's a couple of important equations that are shown here. First of all, the high point in the revenue curve, maximum revenue or maximum total revenue, you can find that by A squared divided by 4B. And remember, the curve of price equals A minus BD. What that'll usually be is A would represent the fixed costs, and then B times D, B would be variable costs times the number of units sold. So in the previous class, we were talking about Cold Stone Creamery. And so the price that they're going to sell for each item has some fixed costs in it, and then it also has variable costs. And so they would have a certain part of their cost is to cover the expenses associated with the freezers and their rent, and then there's a certain part of their cost that has to do with the like the materials themselves, you know, the ice cream like components, the milk, the sugar, the cream, and so on. And so we consider this D hat is the point of maximum revenue. Now, that's not the same as the maximum profit. Profit and revenue are two separate things, as we'll get to in just a minute. But what you should write down maybe in the margin, some important equations that you're going to want to hold on to is that maximum revenue, A squared divided by 4B, and then the demand that's associated with that maximum revenue, D hat, is A divided by 2B. Okay, so back to the idea of costs. The total costs that a business is going to experience are the fixed costs and the variable costs. And so the variable costs, I'm going to go ahead and write on screen here. Hopefully this will work. Variable costs are CV times D. Now, I know this is a bit confusing. This is the terminology the book uses, though, is this is capital C sub V, so that means the variable costs overall, and then lowercase c v, that means the variable cost per unit. And so in an entire month, Cold Stone Creamery's variable costs would maybe be the total amount that they spend on cream, sugar, milk, and so on. But you could know the variable cost per unit. You could know for each individual serving of ice cream the costs associated with that on a variable basis. And if you multiplied that by the number of ice creams sold, then that would tell you the total variable cost. And so it's important for you to know the difference between capital C sub V, which is the overall variable costs, and then that variable cost per unit that was just on screen there. So profit is revenue minus cost. It's the amount that you take in minus the amount that goes out from your business. And so profit is income minus expense. Revenue minus costs. Optimal demand is different from maximum revenue. If we go to the previous slide, this curve, you can see that maximum revenue is whatever price is going to get you the most income. And so why does selling more units have less income? Why gradually will you be making less money even if you're selling more? Remember that to sell more and more and more, you're having to lower the price. And so as you lower the price, demand will go up, but revenue will decrease. So this is the point where you have the maximum revenue. But maximum revenue is not the same thing as optimal demand. Optimal demand is associated with the point, this optimal demand formula. That is where you're going to make the most profit. So D hat is not the same thing as D star. D star is what the business wants to do, is they want to sell the number that gives them the highest profits. It may not be the number that is associated with the most revenue, but what you really like to do is have the most profit, not necessarily the most revenue. Another formula which you're going to need as we go through an example and the in-class exercise that you've got for today is the break-even point formula. What break-even points represent is you need to sell a certain number of items even just to cover the fixed cost. And so it'll tell you that first point at which you're covering the fixed costs. And then the second break-even point is the number at which if you sell it for less than it's costing to make, the break-even point associated with that. So in this formula, I want to point out that it has plus or minus. And so this is going to give you two different values. The plus value is associated with the first break-even point, which is when you begin to turn a profit, and the minus will tell you that last number of items at which you're finally, if you go beyond it, you'll be back into the loss territory. So this is a graphical representation of all of those terms that we've just been talking about. It shows you the first break-even point, and so remember that as we lower our price, more and more people are going to be buying it. And so finally, we've lowered the price so that enough people are buying it, and at this point right here, our revenues are covering the costs. So we've got our fixed costs, and there are variable costs, which when you add the variable and fixed costs together, you get this curve, which is the total cost line. And so the total cost line, when it finally is lower than the revenue line, then there are some profits there. Shaded in gray represent the profits that can be made. And so D'1 is the first inflection point where we're breaking even, and then when you get past D'2, what that means is that you've lowered the price so much that your revenues are declining. Even though you're selling more, your revenues are going down, and your costs still continue to go up, your total costs, because there is a variable cost per unit for every one of them sold. And so you don't want to be any further to the right of D'1 or any further to the left than you want to be right of D'1 and left of D'2, and hopefully you'd be at D star, because D star is the number of units associated with maximum profit. So if you look at the length of that line has the longest length at the maximum profit point, and it's not the same as maximum revenue. So this is showing that you maximize revenue at a different point than you maximize profit. So in the example that we work in your in-class exercise, I'll ask you to actually calculate all of these points for a specific set of numbers. From lecture number 2, this is example 2-4. And in this, we know that a company produces an electronic timing switch that is used in certain products made by other companies. The fixed cost is $73,000 a month, and the variable cost is $83 per unit. The selling price per unit is P equals 180 minus 0.02D. So what we've got so far is already defined for us is in example 2-4. We already know that the cost fixed is $73,000 a month, and we know that the cost variable is $83 per unit. Also defined for us is the function P is 180 minus 0.02D. Now when we see that equation, what we should immediately see is that this has defined A and this has defined B. And so A is 180, B is 0.02. In part A of the example, we're asked to find the optimal volume or the optimal demand for the product. In other words, what's the perfect amount that the manufacturer should sell in order to maximize their profit. And so here we want to find the optimal demand. Okay, from previously we know that the optimal demand, D star, is defined by the formula A minus C sub V divided by 2B. Okay, so we can substitute those values in. A is 180 minus C sub V, which is $83 per unit, divided by 2 times B, which is 0.02. And if you get a calculator and calculate along with me, which I hope that you will. Alright. So we've got 180 minus 83, 2 times 0.02 times divided, and the optimal demand is 2425 units. And so what number does that represent? That represents the perfect number for them to sell, because if they sell more than that, that would mean in order to sell more than that, they'd have to lower their price. And if they sell fewer than that, then they're not selling enough. And so that represents the demand at which they're going to experience the max profit. Okay, so what is the max profit? Since we've just calculated the optimal demand, we might as well get that. Max profit at that demand is going to be the total revenue minus the total costs. And so the total revenue, if we're selling 25 of them, and we know that it's going to be 180 minus 0.02 times 2425. Now what we've just done there is we found out what the selling price is. So we're going to calculate that in a moment. Minus the cost, and our cost function is that it's 73,000 regardless of how many they sell, plus $83 per unit, and we're selling 2425 number of units. Alright, so if we just want to find out what the price is, that's 180.02 2425 times minus, so we're going to be selling them for 131.50. That's our selling price, and then our total costs are going to be $73,083 times the 2425. Okay, so these total costs here are 274,275. So 2425 times our cost per unit of 131.5. This ends up being 318,887.50 minus the 274,275, and so the profit level that we're going to see there is 44,612.50 per month. Okay, part B is we want to know the volumes at which break-even occurs. So, break-even. All right, the formula for break-even is D prime is minus A minus CV plus or minus A minus CV squared minus 4 negative B negative CV square root of that divided by 2 times negative B. Alright. No, you're not going to have to memorize that formula for the exam, but you should know what it means and how to use it. So let's find those break-even points. It's going to be, if we substitute in the values, negative 180 minus 83 plus, for the first root, 180 minus 83 squared minus 4 times negative b, so 0.02, negative c sub v, 73,000, and we're going to square that to 0.5, take the square root of it rather, and divided by 2 times negative b, so negative 0.02. Okay, now here again, I hope that you're not just trusting in my calculations. I hope you'll be skeptical of all the calculations I do and catch any mistakes that I might make. So we've got negative 97 plus, and we'll do all the calculations in there. Okay, so 180 minus 83 squared, 4.02. Now I use reverse Polish notation when I calculate, and so if it sounds like I'm doing calculations in a weird order that you wouldn't do them in algebraic mode, don't be thrown off by that. We will get the same answer regardless. So we'll take the square root. 180, 83 minus squared, 4.02, 73,000. What happens when you talk and calculate at the same time? Okay. Plus 59.74 divided by negative 0.04. So my first root is 932 units per month, and of course, according to this break-even formula, it's to get one root it's plus, and to get the other root it's minus. And so for the other root it'll be negative 97 minus 59.74 divided by negative 0.04. And when we do that, 97 minus 59.74 minus 0.04 negative divided by 3918 units per month. Okay, so again, what does the break-even point represent? This is how many you have to sell in order to just break even and not make any kind of profit. If you sell fewer than that, you're not even covering the fixed costs. And remember, our fixed costs of $73,000 a month, that might be the expense that they have in their lease, the equipment that they have on hand to do manufacturing, and so on. So once they finally produced and sold 932 units per month, finally they've covered those fixed costs. And at the $39.18, in order to get that many, they've had to lower the price so badly that actually if they sell any more than that, they have to lower the price to sell more than that so much that they're actually costing more to produce than they're able to sell them for. The price would be too low. Alright, so part C in this example is sketch curves and label the points. Let me just turn the page here. And so the curves and the points that we hope to see. So we've got an axis that looks like this, and here is volume. It's the number of units sold, and on this axis is cost and revenue. And so this has units of dollars. Alright, so there's going to be a fixed cost. Remember that it's $73,000 a month is how much their fixed cost is, and so we're going to have a line here that represents the fixed cost. And their total costs go up like that linearly, and the slope of the line, of course, represents how many each additional unit costs. And then the curve itself is going to have a shape that looks like this. And so this volume is 932 units, and that is the point at which finally they're into the profit range. And so profit is any time where the revenue curve is higher than the total cost curve. So that's the 932. This is the last one that they can sell profitably at 39.18 units per month. And so you see that the height of this profit is getting bigger and bigger, and so where they've got the maximum profit is not necessarily the highest revenue. The highest revenue, that distance between the revenue curve and the cost curve isn't biggest quite there. In their case, the maximum profit is at the volume of 24.25 units, and so the magnitude of their profit there at that level is 44.612. Okay. And finally, solve by hand and by spreadsheet. So we've just solved that by hand, and I'm going to now start up Excel and solve this by spreadsheet, so you can jump back to the WIMBA lecture, and this concludes the hand calculation portion of this example. Alright, so now you can see Microsoft Excel. If you've never used Excel before, you're in for a real treat, because it's one of the most useful programs that's out there for people in computer science, engineering, safety. It's a great program. I pick this computer program over any other. So we're going to try and solve this same example that we just did the paperwork on. We're going to see if we can find these same things on Excel here. And so the first thing I want to do is enter in the fixed cost. And by the way, you can follow along. You can open up Excel, and I hope that you will, and do the same things that I'm doing, because you need to be able to use these same tools. So we know that the fixed cost is $73,000. Variable cost is $83. A, which is the intercept, is 180, and what the 180 represented is the intercept is if they had zero demand, what their price is, and B, the slope, is 0.02. And so that was in the relationship between demand and price. All right. Next thing I'm going to do is, just as a reminder, I'm going to write what the curve of price and demand was. That was 180 minus 0.02D. All right. So to set up a graph, I want to have D, which is the number of units sold, price, P, revenue, cost, and profit. So what are the formulas for each of those? Let me just insert another line. Okay, the formula for the price was V. I pasted in the formula there for the price. Revenue, the formula for that is price times demand. That's how I can calculate the revenue. It's just the number of units sold times whatever the price is at that point. Costs are going to include fixed cost plus the demand times the variable cost per unit. That will give me the total cost. And then the profits themselves are just going to be revenue minus cost. Okay, so I hope that you're following along with your own copy of Excel. I'll give you a moment to catch up there. Of course, you can pause this at any time or rewind if you want to refresh your memory on certain things. Okay, so demand goes, what we're going to do is go in increments. 0, 100, 200, 300, 400, 500. Let's go in bigger increments. 1,000, 1,500, 2,000. Now, I don't have to type those all in. What I can do is if you highlight a couple of them and then click this down, it will repeat the pattern for as long as I need to go. We'll go to 10,000. So let's just say, in order to get that demand, what price do I have to have? And so the price was 180 minus 0.02 times demand. Okay, so this is the price that I'm charging, and by the way, I'm going to switch this to currency formatting. So let's drag this down in the same way that I dragged before. Anytime you're in a cell, if you see this little box and you click on it and then you drag it down, it's going to fill that in. And so if I have a price of $178, I'll sell 100 units. If I have a price of $176, I'll sell 200 units, and so on. So I'm just going to double click on that corner there, double click, and it'll automatically fill in all of the price and demand. Okay, revenue is going to be equals, is how you start a formula, by the way. And if you just click on the cell and then times that, I don't get any revenue because I didn't sell any units. But if I now double click, that will fill in the formula all the way down. You can see what all my revenues are, and the revenues are declining again because the price is so low. What about my costs? Okay, my costs are going to include the fixed cost of $73,000 plus whatever my demand level is times the variable cost per unit. So my variable cost per unit is $83. Okay, so let me just center that and put it into currency. If I don't sell any, I still have to cover my fixed cost of $73,000. But my costs go up the more I sell. Okay, let me show you something that's important. When I drag that down, it's going to start looking everywhere else. Like, look at the formulas. It was going to 73,000 and 83 before, but when I dragged it down, it started looking in the next row below. And so I need to do something called anchoring. So up here, if I press the F4 button, that's going to put these dollar signs, and now the cell is anchored. And so what that means is that I can drag the formula down, and it'll still be looking up at that original location. The one that I didn't anchor is D, because I always want it to be looking at this, the D of whatever row it's on. So now I can double click there, and that's showing you all of the costs that are associated with increasing level of production. And so now profit is equals revenue minus cost. And you'll see that I haven't made any profit yet. And so if I double click that and have it fill it down, I start to make profit, it looks like, between 500 and 1,000 units. Now from the paper example, we know that the first break-even point is at 932 units. So let me just type that in manually. Instead of saying 1,000, let me say 930. I'll still a little bit negative, 931. Still a little negative, 932. Finally, we've broken even and we're into positive territory. So let's look at, again, if we go down through the profits, it starts going negative again. And we know from the paper example that our second break-even point was 39.18. So let's go here where it's saying 3,500. What about 39.18? And then I type it in, you'll notice that 21,500 switches down to 31.52. And if I do 39.19, I'm back in negative territory again. So we know that the break-even point is 39.18. So the question here was, what we had to actually answer in this example is the optimal volume is where's our maximum revenue. And if we look at what point was the revenue the highest, in the list of those that are shown, it looks like we get 44,500 when we sell 2,500 units. We know from the paper example that it was actually 24.25. So if we type that in, 24.25, we should see it go up a little bit, and it did to 44.612.15. And that is the same profit that we got in the paper calculations. Okay, the last thing I want to show you is that we can create a graph of all of these. That we did the sketch by hand. We can have the Excel make a pretty nice looking graph. And so we're going to do insert and a scatter chart. And the kind of scatter chart that we should select for this example is the smoothed kind here. And so now Excel wants to know a few things about this. So we're going to have to select the data, and we're going to add our X is going to be the number of units sold on the X-axis. So we're going to scroll down through all of the data for the number of units sold. And for the Y, the first line that we should put on there is the costs. So we'll make this our cost line. So we can select here our costs. Okay. All right. So if we go back up to the curve here, what we see so far is our cost curve. And let's just add a couple of things to make this graph a little bit more understandable. First of all, we'll put on an axis title, horizontal axis title below the axis. And so this we're going to call demand D. That's the number of units sold. And on the y-axis, that's just going to be amounts. And the other thing that we want to do is select data. I'm going to edit the name of that. Instead of calling it Series 1, I'm going to call it our total cost. So now in the, you can see how it says total cost. The next thing we want to put on there, we're going to add another series, and this one is going to be our revenue curve, so total revenue. And again, for the X values will be the demand, how much demand we had. And the Y values are going to be the revenue amounts. Okay. So if we go back up to our curve, we see that there's a nice curve there, the shape that we were expecting. And let's also include a profit. The X value is going to be D. And the Y, we're going to do the profit. All right. Okay, now this is exactly right, but what we want to do is zoom in on the portion of the curve that's more interesting to us. And so what I'm going to do, I'm going to right click on, first of all, the x-axis, and right click actually I guess on the line itself. We'll start here on the left one. Format axis, and we want it to start at 0. Okay, and now format axis again. We're going to have it go from, I guess, 0 to maybe 0 to 10,000. Okay. So that looks a lot neater. So let me just expand that so we can get a good view of that. Ooh, it's not quite. All right, so we've got our total cost going up because, of course, there's a unit variable cost associated there. Total revenue, the profits, and so our maximum profit would be where the profit curve is at its highest, and that would be, from the paper example, at the optimal demand of 2425 units. So for those of you who this is your first exposure to Excel, that's probably a lot of information to take in, and don't worry, we're going to have plenty more opportunities for you to get your hands dirty with Excel. But I really do hope that you'll take a few moments to at least attempt what I've just shown on screen there, and we'll have some time on Wednesday in class to take a look at what you've done.